This lecture is an overview on the data encryption standard, which is also known as DES. So we will look at how is the encryption and decryption done in DES and how are the round keys generated. Before that, let's talk a little bit about the history of data encryption standard. So firstly, it is based on the Feistel cipher structure that we talked about, which means that we take each block and split it into left and right halves, and we process the right half, and then we XOR the output of that processing with the left half and do swapping and so on. So DES uses that idea. And also DES encrypts data into 64-bit blocks using 56-bit symmetric key. So we start with that 56-bit symmetric key and then expand that into multiple keys, one for each round. So how did DES become the standard? Well, in 1973, the National Institute of Sciences and Technology thought that we have so many block ciphers around and we need to select one that can serve as the standard for important applications such as banking, ATMs. So they issued a request for proposals for a national cipher standard. Then there were many submissions, one of which was the Lucifer cipher developed by the same team in IBM who developed the Feistel cipher structure. So after analyzing all the submissions, the Lucifer cipher with some modifications was accepted as the data encryption standard in 1977. And it was also published as the Federal Information Processing Standard, publication number 46. And you can Google it and read through this document if you like. This figure summarizes the data encryption standard's encryption process for one block. So we have a 64-bit plain text block. What we do is we first perform an initial permutation on this 64-bit block, which means that we rearrange or shuffle the 64 bits. Then you can see over here that the 64 shuffled bits are processed in 16 rounds. Each round has this round function, which also has some kind of permutation and substitution steps. And then on the right, you can see that for each round, we are also passing this 48-bit round key. And again, these round keys are generated from this 56-bit symmetric cipher key. This is the initial key that both sender and receiver keep secret. And so this is also a shared key. And so DES has its own round key generation algorithm, which takes this 56-bit symmetric key and expands that into 16 round keys. Then the 64-bit output that we have after the 16th round is again shuffled using a final permutation. And so then we get our 64-bit ciphertext block. And so we repeat this encryption process for all the 64-bit blocks that we have in our plaintext. Let's look at the initial permutation step. So for initial permutation, this fixed table is used to shuffle the bits. As you can see here, we have 8 rows, and we also have 8 columns. each number over here is representing which bit to move to that location. So for instance, in the first row, first column, we have 58, which means that the 58th bit in the 64-bit input block is going to move to this first location in the output block. Next, we have 50 written here in the next position, which means that the 50th bit in the input block will move to the second bit location in the output block. And so again, over here, you can see 07 written in the very last bit of 64th bit location here. This basically means that the 7th bit in the input block is going to move to the very last bit location in the output block. So let's see an example. Let's say this is our 64-bit input block right here. And we want to permute this block using this permutation table that we just looked at. So this is that empty output block. Again, this has 64 locations. Try to complete this 64-bit output block using this initial permutation table. So assuming you have tried to complete this table, this is how it looks like after shuffling the input blocks bits using this initial permutation table. So again, you can see here, this is our 58th bit in the input block, right? And the permutation table says that the 58th bit is going to move to the very first location. So 1 is going to be moved here. So we'll put 1 over here. Then we have, this is the 57th bit, 56, 55, 54, 53, 52, 51, and 50. This is the 50th bit, and it says here 50th bit is going to move to this second location. So we have a 1 here, and so on. After the initial permutation, we process the 64-bit block 16 times using 16 rounds, respectively, that you see over here. Now each round has the same operations. Input to each round is the output of the previous round, right? So for the first round, the input is actually the result of initial permutation step, but input to the round 2 is actually output of round 1. And then finally, the output of the 16th round goes to the final permutation step, and the output of the final permutation step is our 64-bit ciphertext block. So let's see what happens inside each round. Also notice that for each round, we are giving it as input our round key, which is 48 bits long. This figure shows what a DES round looks like. You can see here we have a left half and a right half. Now because DES is based on 5-still cipher structure and we have 64-bit blocks, we split our 64-bit block into 2 halves. We have a 32-bit left half and a 32-bit right half, as you can see here. So the round function takes this 32-bit right half along with this 48-bit round key. And these dotted lines here that you can see represented by this rectangle, it's showing you what substitution and permutation steps take place inside this round function. Right, so basically this can be thought of as our round function. right? So again, this round function is taking a round key and it's taking the right half, right? So the first thing that happens is that we perform some kind of expansion / permutation, which basically not only just shuffles this 32-bit right half, but also expands it into 48 bits. So you can see here the output is 48 bits. Then these 48 bits are XORed with the round key. And that's one of the reasons why we need that expansion / permutation step, because we need to have 48 bits. And then the output of this XOR step is then passed through this substitution step. So we have these 8 substitution boxes through which we pass this 48-bit input, and then we actually get back 32 bits. So sort of it is trying to act as substitution / reduction step. And then we have a final permutation step here, which again does some shuffling on these 32 bits. And then again, we have our 32 bits from here. These 32 bits are actually the output of our round function. And if you remember, once you have completed the round function, then you XOR the result with the left half. And once you have done that, then you do the swapping, right? So the right half as is of the current round becomes the left half of the next round. And the output of the XOR function becomes the right half of the next round. And then we process this new left and right half with the same steps that we saw in this round function. So again, the DES round uses a 32-bit left half and a 32-bit right half. And the round function takes the 32-bit right half and a 48-bit round key. First thing to do is to expand the right half to 48 bits using that permutation table. And we will look at that in a bit. Then what we do is we XOR the permuted output, which is 48 bits, with the 48-bit round key. And now we get a set of 48 bits. These are passed through the 8 substitution boxes to get 32-bit result. There is one thing missing here, which is that we also do permutation on the new 32 bits. And so these 32 bits are the output of the round function. Then we XOR those 32 bits with the left half, and then we do the swapping, which means that then the new output that we have becomes the right half for the next round, and the right half from the current round becomes the left half for the next round. So now let's look at the expansion permutation step. Now this step is expanding the bits from 32 bits to 48 bits, and it is also shuffling them. That's why it's expansion / permutation step. So to do that, we use this fixed 8 cross 6 table. So we have 1, 2, 3, 4, 5, 6, 7, 8 rows, and then 1, 2, 3, 4, 5, 6 columns. Just like the initial permutation table, these numbers are telling you where to move the input bits in the new output block. Right, so you can notice here that some bits are repeated because we're trying to do expansion from 32 bits to 48 bits. So actually 16 bits are repeated. For instance, 4, 5, 8, 9, 32, and 1. So the idea here is the same. Now we would move, for example, the 32nd bit from the 32-bit input block and move it to the very first location in the output block, and so on. So again, let's say this is our input block, which is 32 bits, and we want to expand that and also permute that. So we use this fixed 8x6 table because we need 48 bits. So try to fill up this 8x6 table with the new shuffled bits and expanded bits. So assuming you have tried this exercise, you should get this output. Next, we take the output of the expansion permutation step, which is 48 bits. And then we XOR those 48 bits with the 48-bit round key for this round. And so this can be thought of as a substitution steps. Now this will again give us 48 bits. Next, we perform another substitution on these 48 bits. For this, we will make use of substitution boxes, and we have 8 of these substitution boxes. Now the substitution boxes, or S boxes, map a 6-bit input block to a 4-bit output block. So there are 8 S boxes that we use in this step. So the 48-bit input block is then mapped to a 32-bit output block. So these are the 8 S boxes that are used in DES. Each of these S boxes are going to take a 6-bit input, and it's going to give a 4-bit output. All right, so we have 6 bits for the first S box, 6 bits for the next S box, and so on. This gives us 48 bits input, and then we have 4 bits output for each S box, which gives us a total of 32 bits. Let's look at how each substitution box or S box works to substitute a 6-bit input with 4-bit output. So sort of it is also working as a reduction step. So this figure shows the first S box used in DES out of the 8 S boxes. The working is pretty much simple to how we used the Vigenère square to do encryption. So the Vigenère square had labels for rows and columns, and you look in a specific row and a specific column and pick the letter at their intersection, which is the resulting letter that you use as the ciphertext letter. But over here, the only difference is that we have numbers instead of letters. And so just like for Vigenère square, we had labels for rows and columns. Here also we have labels for rows and labels for columns. Rows are labeled from 0 to 3. So we have 4 rows, and columns are labeled from 0 to 15. We have 16 columns. And we look in a specific row and a specific column and pick a number at their intersection. And we convert that number to binary to get our 4 bits. Now, which row and which column to look into is defined by this 6-bit input that we have. So let's say we have a 6-bit input, which is 110010. Now we take the first and the 6th bit. In this case, we have a 1 here, and we have a 0. Right, so we take the first bit and the 6th bit. This is 10. Convert it to decimal, we get 2. Okay. So what we'll do is we will look in the row label 2. Then to choose a column, we take the remaining 4 bits which are these 1, 0, 0, 1, and then we convert it to decimal, which gives us 9. So we will look in column label 9. Okay, so at their intersection, we have the number 12. Now, when you convert 12 in binary, you get 1100, right? So we have substituted 110010 with 1100. So this is 6-bit, this is 4 bits. So pause here and complete this exercise. You have the following S box, and you have a 6-bit input, 100001. So find out what will be the 4-bit output using this S box. So assuming you have completed the exercise, the result is 0001. So what you'll do is you will use the first and the last bit, which is 11, to look in the row. This gives you 3 to look in this row, right? This is row 0, row 1, row 2, row 3. And then you have the remaining 4 bits, which are all zeros. So you convert it to decimal, you still get a 0, which means that you're going to look in this column, the very first one, which is labeled 0. And then at their intersection, you have a 1. So you convert it to binary, you get 0001. Next, we perform another permutation on these 32 bits. So for this, we use this permutation table. And again, the idea is to shuffle the bits using this 4x8 fixed table. So here, for example, the 16-bit from the input block is going to move to the very first location of the output block. And again, the input is also 32 bits, the output is also 32 bits. Next, we take the output of the 32-bit permutation step, and then we XOR that with the 32-bit left half. And after that, we do the swapping, right? So output of this XOR is going to become the right half for the next round, and the right half of the current round becomes the left half for the next round. Next, we have the final permutation step, which is performed only after you have completed the rounds 16 times, right? So once you have processed your 64-bit block 16 times using this round function, then you perform the final permutation. So for final permutation, this fixed table is used to shuffle the 64 bits that we get after the final round, or the 16th round. So as you can see here, we have an 8x8 fixed table here. So we have 64 numbers in this table, and each of these numbers are telling you where to move a specific bit. So for example, in this case, the 40th bit in the input block is going to move to the very first bit location in the output block. So that's how the encryption process works. Let's now talk about how the round keys are generated from that initial key. And we take the initial key and we expand it into 16 keys, one for each of the 16 rounds. So this flowchart explains how the 16 round keys are generated from the initial key. We actually start with a 64-bit key block, which is 8 bytes. And what we do is we actually remove the 8th bit of each of these 8 bytes in the 64-bit blocks. And the reason for that is that we are using these 8 bits just for checking errors. So they are the parity bits, which means that our effective key size in DES is only 56 bits because these 8 parity bits are not really used for encryption and decryption. Right, so again, the first step is that we pass the 64-bit key block through this permutation table known as Permuted Choice 1. And essentially what this does is it shuffles these 64 bits as well as reduces them to 56 bits by actually removing these 8 parity bits. So we take these 56 bits and then generate these 16 round keys from them. So the first step actually is to divide these 56 bits into 2 equal sized blocks. We have a 28-bit left half and a 28-bit right half. And what we do is we circularly left shift these halves by a certain number of bits. Okay, and after we have done that, again we have 56 bits. What we do then is pass these 56 bits through this other permutation table, Permutation Choice 2, which again does shuffling on these 56 bits and also does reduction, because now it only gives out 48 bits, which is the round key. So now we have 1 round key. How do we get the other 15 round keys? Well, this output after doing the circular left shift is again circularly left shifted by a certain number of bits, right? So again, we have a left half and right half. We perform circular left shift on this, these 2 halves by a certain number of bits, and again that output is passed through the Permutation Choice 2, which again gives us 48 bits. That gives us round key 2. Now again, whatever state these 2 left and right halves had, after the left shift, we again take that and perform another left shift on these. Right, so another time we do left shift by certain bits, and the output is again passed through this Permuted Choice 2 table. Unless we have received 16 keys, we just keep repeating this process. Now, and if we have already gotten 16 keys, then we stop the process. So let's look at the Permuted Choice 1 as well as Permuted Choice 2 table. The Permuted Choice 1 PC1 takes 64-bit key and produces a 56-bit key by discarding every 8th bit in the 64-bit key, as well as doing some shuffling. This means that the effective key size of DES is 56 bits and not 64 bits. So the discarded bits are only used as parity bits to check for errors in the key. Now, if there are any errors at this point, then we are not going to generate round keys. We are going to again do the key sharing to get that symmetric key, using which we can then get the 16 round keys. Right, so the 56-bit effective key is then processed to get 16 48-bit round keys or subkeys. Here is the Permuted Choice 1 table. This is an 8x7 table because we are only going to generate 56 bits from this. So some of the bits of the 64-bit keys of the 64-bit key are going to be discarded. So basically the 8, 16, 24, 32, 48, 56, and 60th bits are actually missing from this table because we are actually going to discard them. The working of this table is exactly the same as that of the other permutation tables that we have looked at. So for example, in this case, the 57th bit of the input key block is going to move to the very first bit location of the output key block, which is 56 bits, and so on. Before we look at the PC2, let's look at the iterative circular left shift that we talked about. Now, after we have done the permuted choice 1, we get a 56-bit output, which is then input to a loop that is iterated 16 times, right? So each iteration of this loop generates a 48-bit round key. And in each iteration, a circular left shift is performed on the two 28-bit halves of the 56-bit key a certain number of times. And how many times we do the circular left shift in each round or each iteration is predefined. As you can see over here, in the first round we just do circular left shift by 1 bit. In the second round also we do it by 1 bit. In the third iteration we do it by second bits. In the fourth iteration we do it by second bits, and so on. And the circular left bitwise rotation output of each iteration serves as the input for the next iteration. So basically we started with the 56-bit input, which was divided into two halves, and they were going to be circularly left shifted by 1 bit in the first round. The output of that is going to be again circularly left shifted by 1 bit in the next iteration, and the output of that is going to be again circularly left shifted by 2 bits in the next iteration, and so on. And so after the circular left shift is performed on those two 28-bit halves in each iteration, they are passed through the PC2 or the Permuted Choice 2 table, which is essentially a permutation table, which generates a 48-bit output. So this means that we have 8 rows over here and 6 columns, which gives us 48 values, right? So basically we are doing some shuffling as well as we are doing some reduction. Some of the bits are discarded, and the working of this permutation table is exactly the same as the previous one. Now the DES decryption process is exactly the same as its encryption process, since this is based on 5-still cipher structure. So the only difference in the encryption and decryption is that the round keys are applied in reverse, right? So as you can see over here, again we start with the initial permutation step on the 64-bit ciphertext block, and then we take the output of the initial permutation step and process it in these 16 rounds. And then we are going to do a final permutation on that. And so the only difference is that now the keys are applied in reverse. So we start with the round key 16 and then all the way down to round key 1. And the output of the final permutation step is basically our plain text. Another thing to note is that the key generation process is exactly the same as that for encryption. So we're going to do the exact same steps to get the round keys, but we are going to apply the round keys in reverse. Now, one key desirable property of any encryption algorithm is to have a strong avalanche effect, which means that the change of one input bit or one key bit should result in changing approximately half of the output bits. So basically, DES shows a strong avalanche effect. Now, even though DES itself is secure, it is prone to brute force attack because it has a small key size of 56 bits. And so it was proven in 1998 and 1999 that with some dedicated hardware, you can perform brute force on DES and find the key easily within 22 hours. So at that time, it was 22 hours, but now it's way faster. So therefore, to improve the key length of DES, it was proposed that we should encrypt a plaintext with DES multiple times with different keys, right? So we have several options here. We can do double DES, which is basically applying DES 2 times, but each time with 2 different keys. Then we also have triple DES, either with 2 unique keys or triple DES with 3 different keys. Let's look at double DES first. Now this figure shows the encryption and decryption process for double DES. So here you use 2 different 56-bit keys. So you encrypt the plaintext with the first key and then encrypt the result of that, shown by X here, using the second key. And the same thing for decryption. For decryption, now you take the ciphertext decrypted with the key 2 first, so you apply the keys in reverse, and then the result of that, referred to here by X, is again decrypted using key 1 to get back the plaintext. So here, basically, the effective key size now is 112 bits instead of 56 bits, because now you have 2 56-bit keys. Right, so if now you want to perform brute force attack, you need to do 2 raised to power 56 into 2 raised to power 56 operations, which is equal to 2 raised to power 112 operations for brute force attack. Because for each first key, there needs to be 2 raised to power 56 possible second key, right? So you need to perform 2 raised to power 56 operations for each first key, which essentially becomes a total of 2 raised to power 112 operations. But the problem is that double DES is actually prone to an attack known as meet in the middle attack, which tries to reduce the brute force attack to just 2 raised to power 57 operations. Right, so the attacker can perform brute force attack with just these many operations instead of these many. And so the meet in the middle attack is one of the reasons why data encryption standard was replaced with triple DES and not double DES. So let's take a look at what meet in the middle attack is. This is actually a known plaintext attack, where the attacker has access to plaintext ciphertext pairs, so they know some plaintext and also its corresponding ciphertext. For example, a constant file header value. They know what it basically is, and they also have access to its corresponding ciphertext value. Right, so we always have plaintext ciphertext pairs in this type of attack. Now, what the attacker does is they first encrypt the plain text using all possible 2 raised to power n keys. Here we have an n-bit key length, and stores the keys and their ciphertexts in a table. So let's assume that our plain text and ciphertext is a 5-bit block each, and let's say this is one pair. We have a plain text 01101 and a ciphertext all ones, and this is, let's say, a plain text ciphertext pair that the attacker has access to. And for simplicity, let's just assume that the key size is 3 bits. So the attacker will compute ciphertext using all possible 3-bit keys with the cipher. So this table here shows sample values resulting from encrypting this plain text in this pair with all possible 8 keys, because we have 2 raised to power 3 possible keys here for a 3-bit key. So the attacker is going to encrypt this plain text with all these 8 possible keys and going to store their corresponding ciphertext values. So let's just assume that this is the table that they get. The attacker then decrypts the ciphertext in this pair using all possible 2 raised to power n keys, again with n-bit key length, and then stores their corresponding plain texts with the corresponding keys in another table. So let's say this table here has the plain text resulting from applying all possible 8 keys for a 3-bit key value on our ciphertext, which was all ones in that plain text ciphertext pair. And so we refer to these plain text values as X values, just like previously here, all these ciphertext values are referred to as X. So notice here what we have done so far is to perform encryption from one direction. Right, so we did this to get the first table. So we had our plain text and ciphertext pair. So we took the plain text and performed encryption on it using all possible K1 keys, and we stored it in the table, and then we have those all possible X values. And then we performed decryption from the other direction, right? So we took the ciphertext in that pair and we decrypted that ciphertext using all possible K2 values, right? Which would give us again X, right? So encryption on the plain text and the decryption on the ciphertext. So both these operations result in the same X values, which is what the meet in the middle means. So you're trying to meet in the middle here. So what the attacker does next is to compare the two tables that he computed from these two operations and see for which two key values the X value is the same. Right, so these two key values are K1 and K2 respectively. Here are the two tables from the example we just used. Notice here there are two instances where X value is the same. One is when key 1 is 001 and key 2 is 100. Right? For each of these, we get the X value 00111. The other is when key 1 is 011 and key 2 is 111. Right? In both these instances, we get the X value 01000. So both of these pairs are candidate key pairs that could be the actual keys. Right? To verify which one is right, the attacker uses them on another plaintext ciphertext pair that they have access to. So they would apply a key 1 on the plaintext, and then the result of that they will apply a key 2 on, and then see if the resultant value is the same as the ciphertext value in that pair. If yes, they have found the right key. They would try it on these candidate key pairs. Right, and that's how the double DES works, right? You take your plaintext, you encrypt it using key 1, you get some X value, and then again you encrypt this X value, you again encrypt it using key 2 value to get your ciphertext. So if we take a look at how many operations it took for this attack, we can see that we just needed 16 operations. 2 raised to power 3 or 8 for encryption table, and then 2 raised to power 3 or 8 for the decryption table. We also did a few more encryption steps to check that the 2 candidate key pairs are the right key pairs or not, but those are a small number of operations. You can add them as well. But if we were to perform brute force attack, we would need a total of 64 operations in this example, since for each 8 values of key 1, we will need to try all 8 values of key 2, right? That's 2 raised to power 3 into 2 raised to power 3 or 64. Right, so meet in the middle attack was 2 raised to power 3 plus 2 raised to power 3, which is 16. But brute force attack would be 2 raised to power 3 into 2 raised to power 3, which is 64. Because for each key 1, let's say 0, 0, 0, then you would need to encrypt the result with all possible key 2s. Right, so 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. 8 values. And then again, for the next possible value of key 1, 0, 0, 1, you would again try all possible 8 values of key 2. So that's 2 raised to power 3 into 2 raised to power 3. So we can generalize this. We can say that meet in the middle attack on double DES reduces brute force attack from 2 raised to power 56 into 2 raised to power 56 to 2 raised to power 56 plus 1, or 2 raised to power 57. Because if you think about this one, this is technically 2 raised to power 4, or 2 raised to power 3 plus 1. So this is 2 raised to power n into 2 raised to power n, and this one is 2 raised to power n plus 1, which is a way smaller number as compared to brute force attack. So due to the meet in the middle attack on double DES, the data encryption standard was replaced with triple DES and not double DES. Now, triple DES uses 3 56-bit keys, resulting in an effective key length of 168 bits. So now for brute force attack, we need 2 raised to power 56 into 2 raised to power 56 into 2 raised to power 56, which is 2 raised to power 168 operations. Meet in the middle attack is still possible, but it is more complex as compared to double DES. Note that we can use either 2 unique keys or 3 unique keys, as you can see over here. This figure is using 2 unique keys for triple DES. This figure is using 3 unique keys for triple DES. So if we are using just 2 keys, what we do is we apply key 1, the result of that we apply key 2, and then the result of that we again apply key 1. And if we're using 3 different keys, then first we apply key 1, and the result of that encryption using key 1, we apply key 2, then the result of that we apply key 3, and so on. Another thing to note here is that during encryption, we use an encrypt, decrypt, and encrypt process. And this is used for backward compatibility with systems that are just capable of simple DES. So always in the second step, we apply DES in the decryption mode. That is for the encryption process. Then for the decryption process, we use decrypt, encrypt, then decrypt. Right, same thing over here, even with 3 different keys. For encryption, we first use DES with the first key in encrypt mode, then we use DES with second key in decrypt mode, then we use DES with third key in encrypt mode. And correspondingly for decryption, with key 1 we use the decrypt mode, with key 2 we use the encrypt mode, and then with key 3 we use the decrypt